of G, and this and G sigma is equal to really, in this case it will be SON. So hence this SUN comma SON is a Riemannian symmetric pair, and this SUN mod SON is a RSS. Okay, and this SUN mod SON is a different symmetric space than UN mod ON. So you should not really you just if you compare the dimension, then you will get it. So now see example C again. So let G is equal to really SO2N and define the sigma from SO2N to SO2N by this thing, by sigma of A is equal to JA J inverse. So what is J? J is the standard complex structure on R2N, where J is the standard complex structure of R2N. R2N, and what is the precisely this J is equal to really 0 I minus I 0. Okay. Since J belongs to O2N, J is a O2N, and this J square is equal to minus identity, and this is sigma is the conjugation by J, so it is easy to see that sigma is an automorphism of SO2N. SO2N, and the sigma square is equal to identity. Now, so sigma A is equal to A. This is equivalent to the fact that J inverse is equal to really A. So that will imply that J is equal to really AJ. And that means J A commutes with the complex structure. This is equivalent to this fact that J belongs to GLNC. Okay. And remember, we have really shown in the past class or first or second class, GLNC is equal to S belongs to GL2NR. So that Xj is equal to Jx. So I am using that fact. So A belongs to GLNC, and A is also an element of SO2N. This A belongs to GLNC intersection. So hence we get this thing. Hence, so what? Hence G sigma. This is really SO2N intersection GLNC. And in some class we have shown that this is actually UN. We have seen this thing. We have proved that this is UN. Hence this thing SO2N comma UN is a Riemannian symmetric pair, and this thing SO2N mod UN use a RSS. So this was the thing. Now I want to really prove. Last lecture I commented that, so all of you know that G is a compact Lie group. Okay. Compact Lie group, then G is a Riemannian symmetric space. Okay. And
connected.
Yeah. G is a connected compact Lie group. Then G is a RSS, G Riemannian symmetric space. So we want to determine the Riemannian symmetric pair corresponding to this. So for that we need to know a little bit of some Lie theory, little bit. Okay, so let us do that. So first I want to really prove a proposition like this thing. So let G be a connected Lie group. Then G is actually sigma compact, and the second counter. So So we will only use this fact that G is sigma compact, but something more is true. So proof is since G is connected, therefore G can be written as, so n belongs to n, some k to the power n, where k is a compact symmetric neighborhood of identity in G. This is identity in G. So this is the usual way that in a topological group, neighborhood of identity generates the whole group. This is the usual argument. So since for each okay, since for each n belongs to n, this k to the power n is compact. Therefore, okay, therefore G is really sigma compact. Okay, so here we are using this connectedness of the Lie group, and G is second countable. I am leaving that thing. So that is also easy. So that second, this is a really I am putting it as an exercise. Okay. So this is the thing. Now, one fact about Lie group. So fact one. So let G be a connected abelian Lie group. So then G is diffeomorphic to this thing S1 cross S1 cross something like R to the power n, R to the power n. So this is a k times, and this is a diffeomorphism. This thing is diffeomorphism. So second thing is let G be a compact connected abelian Lie group. So there will be no Euclidean part because the group is compact. So then G is equal to S1 cross S1. So this is k times. So where in this case, what is k? K is equal to real dimension. So this is actually diffeomorphism. So you can see, you can find proof of these two facts in any Lie group because this is a very standard result. For proof, you see any book. So okay, so now this is the thing. Now second fact I will use. I have to, so let G be a connected Lie group. So then G is abelian if and only if its Lie algebra is abelian. And connectedness is really an important assumption here. So for example, this O2 um, is not abelian, but its Lie algebra is abelian. So connectedness is an important assumption here. Okay, so this is the thing. Now I want to talk about a little bit of adjoint representation. Okay, so let us try to the discussion. So let G1, G2 be two Lie groups with Lie algebra of G1 is really small G1 and Lie algebra of G2 is really G2. Then this thing G is equal to this G1 cross G2 is a Lie group with Lie algebra G1 cross G2. Now for this G1, G2 belongs to G1 cross G2. Okay, define this. Okay, so for this G1, G2, we know that this. So I G1 cross G2 is a map from G1 cross G2 to G1 cross G2 given by this thing. Given by I is okay. Given by this thing I G1 G2 applied on H1 H2. So this is really G1 comma G2 H1 H2 G1 comma G2 inverse. So this is really G1 comma G2 H1 comma H2 G1 inverse and G2 inverse. So this is G1 H1 G1 inverse G2 H2 G2 inverse. So that means this is I G1 of H1. So I G2 of H2. Now, so therefore I can take the derivative of I G1 and G2. So taking derivative, so we get this thing. So derivative of Ig is really Rg, right? So we will get this R of G1 cross G2, G1 G2, and this is right hand side is the you can write so in the right hand side we'll get R of G1 G1, R of G2. Now this shows that from this you call this as star. Okay, so from star it is clear that this thing if H1 is a subgroup of G1, so this is the notation for subgroup in the group theory. So H1 is a subgroup of G1 and this H2 is a subgroup of G2. So that will give you this R of G1 cross G2. This is H1 H2. This is really diffeomorphic to R G1 H1 plus R G2 H2. So this is a thing. Now the thing is again discussion little okay. So definition. So let G be a Lie algebra over K. Okay, where K is equal to the R or C. So a vector subspace, this H of G is called an ideal if this thing happens. Lie bracket of H and G is contained inside H. That is if X belongs to H and Y belongs to G, then this implies this Lie bracket of X, Y belongs to this is H. So now clearly, so any ideal of G is a subalgebra of G. However, this converse is not true. Converse is not true. So for example, you can see that example this SLNR is an small SNR is an ideal in GLNR. So second thing, SON, this is a sub-algebra of GLNR, but not an idea of GLNR. But not an idea. So this is the thing. Now I have to give another definition. So definition. So AZ algebra G is called simple if it satisfies the following satisfies the following two conditions. So first thing is dimension of G. You have to assume this is greater than 1. Second thing, that G has no proper ideals. In no proper ideals, except that means the only 0 and G are the only ideal, except 0 and G. So now another definition. So, a Lie group G is called simple. G is called simple if and only its Lie algebra is simple. So Lie algebra of G is simple. So this is the thing. Now the thing is, okay. So I really, this is my definition of simple Lie algebra. Okay. Now, so okay, discussion. So okay, observation. Let us see. So let G be a connected Lie group. Lie group with this thing dimension of G, and this is equal to really a dimension of Lie algebra. This is equal to 1. Okay. So if that is the case, then G is abelian. So that means we have shown that if Lie group is connected Lie group is abelian if and only if its Lie algebra is abelian. So it's saying that Lie algebra is abelian. Okay. Since this G is abelian, this implies G is abelian. Okay. And by therefore either G is really some product of this S1 cross R to the power m, but since dimension of G is 1, okay, so that means either G is equal to really S1 or G is equal to R. So what I am saying that if a Lie group, let G be a Lie connected Lie group which has dimension is equal to 1, then either that will be S1 or that will be diffeomorphic to R. So this is diffeomorphism in fact. So these are diffeomorphism. Okay, so now let us see the discussion. So let G be a Lie group. I am not assuming this is connected now. So I am not assuming this is connected. Let G be a Lie group with a Lie algebra. So let H be a subspace of G. So invariant under this adjoint representation. So that will imply that. So what does that mean? That is, this implies. So this is equivalent to the fact that R G G, this H is really a subset of H. Okay. Now H is an
If G subspace of
what?
K be a subspace of G, capital G.
Oh, cos subspace of small g. Thanks. Lie algebra. Okay. Short G's. So I have told you in the context of a Riemannian symmetric pair. If this is the case, that in the context of Riemannian symmetric pair, I have told you something like this. So if G, comma H is a Riemannian symmetric pair, in the context of symmetric pair, and this was the thing that R G H of P is subset of P, then I have derived this equation. From the here I have derived this thing, this K P, Lie bracket of Kp is subset of P. Okay. Where what is K? Where this K is really Lie algebra for H. And also I have told you that converse is also true if H is connected. If H is connected, okay, H is connected. This converse implication also true. Converse is also true. Okay. So I am using that thing. So if you will use that similar kind of argument, actually it is the same proof actually. So this will imply that G, Lie bracket of GH is subset of H. That will imply that H is an ideal NG. Okay. Now for converse, you need this H is connected. So hence, so conversely, if G is connected and H is an ideal NG, so that will imply that this will imply that so RG G H is really contained inside H. So hence, if G is connected, RG invariant subspaces of G, subspace of G are precisely ideal sub G. Ideal sub G. So hence, if G is connected, RG invariant subspace of G are precisely ideal sub G. So that this so that so I want to investigate the situation when this adjoint representation is irreducible. So hence RG action on G is irreducible. So that means irreducible means this will have no non-zero idea, okay? And that happens in two cases: reducible, if and only.
Is there any simple assumption somewhere which I'm missing?
Where?
Why is it irreducible? I missed it.
No,
Are you
I am saying
assuming
that.
something is simple?
No, I am saying that if RG action is on G is irreducible means that what? This means that there will be no proper ideal sub G.
Okay, if and only if. Okay.
And only. So there will be no proper ideal sub G. So this happens in exactly two situations. happens in exactly two situations. So first condition is really either G is equal to H1, G is equal to R, or G is equal to H1. Actually, this is diffeomorphic to R, but I am writing this H1. This is actually diffeomorphic. Okay, so and second thing is really G is simple, because in this case of simply the definition of simply algebra, we have really excluded that condition, that dimension of G equal to 1 condition. We have really removed that. For that reason, there are two cases. Okay. So hence RG action is on G is reducible if and only if G is either isomorphic to R, or G is isomorphic to H1, or G is simple. Okay, so now we go to the discussion. This is the case. So we have proved a much more general result. So G be a connected Lie group with RG is compact. We have proved a much more result. This is compact. Then we have shown that in any bi-invariant Riemannian metric, on G, G becomes a Riemannian symmetric space. And what was the geodesic inverse? So precisely this geodesic inversion SC at point G was G inverse, and SXG is really X G inverse X. This is we have derived this thing. So observe one thing. This in this setup, in this specific example, this geodesic inversion really doesn't really depends upon this choice of bi-invariant Riemannian metric. And that is also, I have told you in the case of a Riemannian symmetric pair also, when I proved this theorem that given a Riemannian symmetric pair, we can associate a Riemannian symmetric space. Then also I tell that the Riemannian metric will not really depend upon, sorry, the geodesic inversion will not depend upon the choice of Riemannian metric. So and this is also clear from this example, or this observation. So in this specific example, the geodesic inversions doesn't depend upon the choice of bi-invariant Riemannian metric. And this is a really so okay. So this is the thing. Now what you do, and we have also seen that this really is a bi-invariant Riemannian metric on G. So matrix on G is really 1-to-1 correspondence with really RG invariant Riemannian RG invariant inner products on G, Lie algebra. So that means so how do you construct a bi-invariant Riemannian matrix on G? So you fix a bi-invariant, sorry, you fix an RG invariant Riemannian RG invariant inner product on G. This is RG invariant. So, this is RG invariant. So you define this Q is by this inner product and use the left translation G to really define the Riemannian metric on G. Okay. So this is the way we have done. Okay. So it is clear that in the previous lecture I have asked this question: when does this bi-invariant Riemannian matrix on G is unique up to scalar multiple? Okay. So now I am answering this question. It is clear that if RG invariant RG acts on G irreducibly, okay, then there will be exist a bi-invariant Riemannian matrix on G uniquely up to scalar multiple. So hence it follows that if the RG action on G is on G, RG action on G is reducible, so then there exists a unique bi-invariant Riemannian metric on G up to scalar multiple. So this was the question which I asked in the previous. You can look at page number 409 or something. I am not showing that, but this was the question I have still asked. And when does this happen? This happens if and only if. So first condition, either G is really S1 or G is equal to R, or G is simple. So let us write this R. Okay, so this happens in two conditions: if G is equal to S1 or G is equal to R, or G is equal to a simple Lie group, then there exists a bi-invariant Riemannian metric on G up to scalar multiple. This is clear, right? So now, okay, so now let us write the conclusion. So let G be a connected Lie group with RG is compact. So I am writing this just then in any bi-invariant matrix, G is a Riemannian symmetric space. Moreover, if actually G is equal to S1 and G is equal to R, these are some simple cases, so I am leaving those things. Moreover, if G is a compact simple Lie group, so this part is important. If G is a compact simple Lie group, so then the isotope representation is irreducible. And there exists a unique bi-invariant Riemannian metric. Metric on G up to scalar multiple. Okay, so this is a very important example, compact simple Lie group. We will use probably, hopefully, this observation later. So now I want to describe its Riemannian symmetric. So what we will do, we will describe the Riemannian symmetric pair. So now what I suggest that you just forget what you have learned about this type of results. We will prove we will first describe a Riemannian symmetric pair, and using that we will prove this result in a different way. So I am saying that you just forget this result. There is a connection between correspondence between bi-invariant Riemannian matrix on G and RG invariant inner product on G. This result you forget, and you also forget that you have not proved that this result, that if G is a connected Lie group with RG is compact, then G is a Riemannian symmetric space. You just assume that you do not know this result. Okay? So we will do the things in a different way. Okay. So discussion. So let G be a connected Lie group. Okay, so then G acts on G by both in left and right translation. So let G tilde is equal to G cross G. Okay. Then G tilde acts on G by this thing. If you take A B dot G, this is really A G B inverse. So we are multiplying from left and right from by B inverse. So this is both. So there is so both translations I am taking. Okay. Now, if you look at this thing, this is the group action definition. If you look at this A B dot A E dot E, so that is really A E E inverse. This is really A, and so that means E and A, these are in the same orbit, and that means this group action is transitive. So thus the group action is transitive. It's transitive and also smooth. Smoothness is very clear because this is left and right translation. So let this thing delta G cross G. This is really GG, so that G belongs to G. Okay, so this is my definition, and this is a really isomorphic to where? This is isomorphic to G, right? Okay, so this is isomorphic. And this delta G cross G is called diagonal in G cross G. Diagonal in G cross G. Okay. Now, okay, so let this thing, let H is equal to H tilde is equal to stabilizer of E inside G tilde. So A B belongs to H tilde. So that is imply that this is equivalent to the fact A B dot E is equal to E. This is equivalent to the fact A E B inverse is equal to E, and therefore you will get this A is equal to B. So if A B belongs to H tilde, then A has to be B. Therefore H tilde, what is H tilde? H tilde is equal to this diagonal of delta of G cross. Thus Pustida, is it clear so far? I think Mithunda, is it clear?
Yes, Muna.
Okay, so this H tilde is equal to delta G cross G. Okay, so now I have told you that this action is transitive. So we expect that G tilde by H tilde. So you expect that G tilde by H tilde is really diffeomorphic to G. Okay, because the action is transitive and there is arbitrary relation. But this happens this doesn't happen usually. But I told you that there are three conditions when this happens. That if this G tilde is compact, okay, or G tilde is really sigma compact, and or this G tilde is really second countable. Second countable. In these three conditions, you can say that this is really deformable happens. So this G tilde is sigma compact is the most general situation, and third condition G tilde is second countable is the most popular. People actually use mostly this third condition. So that is the thing. So now, but since G tilde is connected, because G is connected, since G tilde is connected, therefore this implies G tilde is sigma compact or second countable. If you want, like, you can put also second countable if you like that condition very much. So therefore this alpha from G tilde mod H tilde to G given by alpha of AB H tilde. This is really AB dot E, and this is really AB inverse is a diffeomorphism. Okay, so this is a diffeomorphism. So let phi from G tilde to G tilde by H tilde be the canonical projection. Canonical projection given by this thing. Pi of this E is really O. Oh, pi of AB H is equal to AB. No, pi of AB is really, sorry. This is really AB H. AB H tilde. So let pi of E is equal to O. Then with this notation, pi of AB is really, this will be AB dot O. Now, okay. So this is the thing. Now this thing is okay. So now onwards we will assume that RG is compact. So okay. So okay. Let another thing is I have to let beta really alpha composition pi be a map from, this is a map from where? This is a map from G tilde to G. Okay. Then this beta is given by beta for AB. This is really pi alpha composition pi of AB. So this is really alpha of AB dot O, and AB dot O will go to AB inverse. Beta of AB is really AB. Okay, so now onwards, we assume that RG is compact. So I am writing this way because there are several groups, so I am writing this RGG is compact. Okay. So define. Okay, now I am constructing this map sigma and Riemannian symmetric. Define sigma from G tilde to G tilde by sigma of AB is equal to BA. Okay. Now the thing is, if this cardinality of G is greater than 1, then G will contain at least two elements where A and B are different, and then sigma of AB is clearly not equal to AB. because sigma phi b is equal to ba, and we have chosen this a and b are different. Therefore, if g mod g is greater than equal to 1, then this thing sigma is not equal to identity, and also it is easy to check that this thing and sigma is an involutive automorphism. Okay, involutive automorphism. Now, okay, so we want to really find out the G sigma. So sigma of AB is equal to AB if and only this BA is equal to AB. So that means this is if and only if A is equal to B. So hence G sigma is what? Hence this G sigma is really H tilde. And what was H tilde? This was the diagonal of G cross. And this H tilde is really isomorphic to G. This is isomorphism. Therefore, okay, therefore corrected. So this is really, therefore this implies this is connected. Because G, we have assumed that this is connected. Okay, now I want to really prove what is this odd G tilde H tilde. Okay, so let G belongs to H tilde because this, okay, so this odd of G tilde G, this is really odd. G tilde is what? G cross G, G. So this is really same thing as odd of G and odd GG. So if you look at this thing, they say star or double star. So from this double star, it is clear. Double star. It is clear that this thing, that this odd of G tilde S tilde is isomorphic to this is odd G. This is isomorphism, group isomorphism. Everything is this group isomorphism. Since this odd GG is compact, odd GG is compact. Hence, this R G tilde S tilde is really compact. So therefore, hence G tilde S tilde is a Riemannian symmetric. Now, therefore, Riemannian symmetric pair. Also, this is a Riemannian symmetric pair, and so G tilde H tilde is a Riemannian symmetric. G tilde mod H tilde is a Riemannian symmetric space. Now this alpha from G tilde by H tilde to G is a diffeomorphism. Okay, so what we will do, we will transport the Riemannian structure from G tilde H tilde to G, and geodesics according to G, and if you will transport over everything to G, then G becomes a Riemannian symmetric space. It is clear. Okay. So remember, I told you in the beginning, you do not know this result as G is a Riemannian symmetric. You are proving this thing in a different way. So you just forget everything. Okay. So under this via alpha, so the group, so action of G tilde on G mod S tilde. This actually, if you this is just so how does this G tilde acts on G tilde on G G tilde by S tilde. This is just the usual. This acts on by left translation, right? But on G, it acts from both left and right, right? Action of G tilde and G tilde S tilde corresponds to left and right translation on G. Hence, any on G via the map alpha, via alpha. Hence, any G tilde invariant Riemannian metric on this thing, metric on G tilde mod H tilde. This corresponds to, okay, pay attention here, since this on G this action transfers on G this action corresponds to both left and right. So any G tilde invariant Riemannian metric on G tilde by H tilde corresponds to a bi-invariant Riemannian metric on this. Riemannian metric on this. Hence, there exists a one-to-one correspondence between the following two sets. This is really so, but G tilde invariant Riemannian matrix on G tilde mod H tilde and this thing by invariant Riemannian matrix on G. Now we know that from our abstract theory that there always exists G tilde invariant Riemannian metric on G tilde. Hence, we have shown that so that if RG is compact, so there always exist a bi-invariant Riemannian metric. So Riemannian metric on G. Okay. So this is the thing. Now I want to really determine this so-called geodesy inversion on this G. So on G tilde by S tilde, this is we have it is a Riemannian symmetric space, and on G I want to really transfer the everything to G. So between this G tilde to G there is a map alpha, and this is the corresponding AB dot O. Under this alpha, this will go to AB inverse. So G dot O, this will go to really G. Okay. Now I want to really find this SXG, where X belongs to G, G belongs to G. Okay. So under this thing, this will actually correspond to what? This will correspond to X, okay, XC dot O to GE dot O. Okay. So this will correspond to that. Right? So if okay, so first you need to find this thing X of XC dot O and GE dot O, because X, and I have told you that if G comma H is a RSP, Riemannian symmetric pair, then this is really SO. Okay, G dot O was really nothing but sigma G dot O, and S of X G dot O. Okay, S of X dot O and G dot O. This is really X SO dot X inverse G dot O. So this was the thing which we have shown that. So you want to use that thing. So this is really XC. So I am using the last one. I am using this one. So this is XC SO XE inverse. Okay, this is GE dot O. Just write the formulas which you have known. This is really XE. So X dot SO XE inverse is really X inverse E, and this is really GE dot O. So if you really multiply if you will take care of the first action, this is the group multiplication. So this will be X inverse G E dot O. So now you apply the first thing, XE dot SO X inverse G E dot O is the sigma of X inverse G E dot O. Okay. So this is really XE dot. Okay, so sigma of X inverse G is really E X inverse G dot O. Now you explore the definition. This is X E dot X inverse G. This is X inverse G dot O. Now, if you look at this thing, A comma B dot O, this will correspond to AB inverse. So this fact, this chap, so this chap will really corresponds to this thing. This is really X inverse G inverse. So this is X G inverse X. So this is exactly the same thing which we have got for this the case of which we have got. Okay, this matches with the previous thing. Okay, so we are getting this thing now. Tapendu, is it clear? Or?
Yes, ma'am.
Actually, I am discussing this example because this example is a very important example. Later on, we will use everything. So now I want to define an. This is a Cartan decomposition. So let xy belongs to really G cross G. So theta of xy, this is really, so d sigma E xy. So that is really d by dt of t is equal to 0. This sigma of exponential of tx, exponential of ty, and sigma of ab is equal to ba. So this is really d by dt. T is equal to 0. This is exponential of ty into exponential of tx, right? So that will show that this is really yx. So then what was k? But k was by definition. This is xy belongs to g cross g. So that theta of xy is equal to really xy, right? This is the plus one eigenspecies. Now theta of xy is really your yx, and this is yx. This will be, we will get that yx is equal to sy. So this is equivalent to the fact that x is equal to y. Okay. So what we will get this, therefore we will get that k is equal to really x belong. Okay, k is equal to, this is x, so that x belongs to g. So similarly we will get what p is equal to really xy belongs to g cross g. So that theta of xy is equal to minus of xy, right? Okay. So now this is the thing. So theta of xy is what? These are really yx, right? So yx is equal to really minus of x and minus of y. Okay. So that will give you what that will give you y is equal to minus x. So therefore p I will get y is really x minus x. So that x belongs to g. Okay. So observe that these are really identified. You can identify this to g, and you can also identify this p with g. So precisely this x minus x going to x is an isomorphism from p to g. Okay. So this is an isomorphism from p to g. Now I want to talk about so-called adjoint representation. Okay, isotropic representation. Let us write isotropic. So the thing is, we already know that isotropic representation of H tilde. Okay. So isotropic representation of H tilde is equivalent to add G tilde S tilde action on P. Okay. So let GG belongs to H tilde because H tilde is a diagonal, and this x minus x belongs to P. Okay. So that means add G tilde GG applied on x minus x. So this is really this is same thing as R G cross G GG on this x minus x. So this is really same thing as R G G x, and so minus of R G G. So now observe that okay, so what was the isomorphism from P to G? X comma minus x to x. Okay, this remember this isomorphism. Okay, so we know that this thing. So this R G tilde S tilde. So this was really isomorphic to RGG. So I have proved somewhere in the when I proved that this is really RG tilde is compact. So this is isomorphic to, and this P is really isomorphic to G. Okay. So this RG tilde S tilde has an action on P. This action on P, and this acts on G, and there are some isomorphism. Okay, if you look at this triple star, say from triple star, it is clear that this. So these are really isomorphism. This is isomorphism. So from triple star, it is clear that this thing. So RG tilde S tilde action on P is equivalent to RGG action on G. Hence, so that is the thing. Hence, we what we get. Hence, we get. Okay. So G tilde invariant Riemannian matrix on G. This was really this was one-to-one correspondence with what? This was an one-to-one correspondence to with R G tilde S tilde invariant inner product on what? On T naught G tilde by S tilde. This we have seen by abstract theorem, and this is really now since this R G tilde S tilde action inner product. Okay, okay, sorry. This is R G tilde invariant inner product on T naught G mod by S. This is not T1. This is really on P. So this is now this R G tilde S tilde invariant inner product. Oh, okay. So this is the thing. So this is actually G tilde invariant Riemannian matrix on G tilde mod S tilde. Okay. So this is really equivalent to the fact that R G tilde S tilde invariant inner product on P. And this action is really is equivalent to RGG action on G. So this is one-to-one corresponds to it really RGG invariant inner product on G, right? And this was really and G tilde invariant Riemannian matrix on G tilde by mod S tilde. This is one-to-one correspond with by invariant Riemannian matrix on G. So hence from here actually you will get hence you will get that this is there is a one-to-one correspondence between this and this. Hence we see that there exists a you see that there is a one-to-one correspondence between there exists one-to-one correspondence between this bi-invariant Riemannian matrix on G. And this is really RG invariant inner product. So this is we are really proving everything in a different way. Okay, so this is a different way of proving the same thing which we have shown. So hence there exists a one-to-one there exists a okay, hence the isotropy okay, hence the isotropy representation is reducible if and only if so RGG action is reducible. And therefore there will exist unique bi-invariant Riemannian matrix on G of Tosca. I am not writing this. Thus we have proved the following. Proposition. Let G be a connected Lie group with RG compact. Then G cross G delta G cross G is a Riemannian symmetric pair with involution sigma of AB is equal to BA. Okay, so and the corresponding Riemannian symmetric space is G. Split is really G. Moreover, actually same thing. Moreover, if G is simple, okay, is simple and compact, the isotope representation is reducible. Representation is reducible. So I want to finish one or two things. Sir, will I continue just one small example? I will stop. SKR, sir. Are you there?
You are asking me. You are asking me. Yeah, continue.
Will I continue? Once, just small example, or in the next.
Yeah, it's your lecture. Continue.
No, people will not like. Okay, in the next lecture, then I will give some example. More. Actually, in the next lecture, what we will do is something like this thing. CGH is a Riemannian symmetric pair. So we have seen that whatever example we have produced, this H is really compact. Okay. In the next lecture, we will see that some example where H is small, non-compact, and still then GH is a Riemannian symmetric pair, and we will also see that infinitely many Riemannian symmetric pair, this may give rise to the same Riemannian symmetric space. So with this I would like to stop, and if there is any question you can ask me.
Muna, I have a question, but not really closely related to this lecture, but somewhat related.
Yes,
I have the following question: that I look at the pair G tilde H tilde, which you have defined.
Yes, sir.
H tilde is the diagonal.
Yes.
Now this is clearly a Gelfand pair.
Yes.
Now I look at the Riemannian symmetric space G tilde mod H tilde.
Yes, sir.
Which is basically G.
Yes, sir.
Now I want to look at differential operators on G tilde mod H tilde, which are left invariant under G tilde and right invariant under H tilde.
Yes.
That would be a commutative algebra because it's a Gelfand pair.
Yes.
Now those differential operators are related to differential operators on G.
Yes.
Which operators?
Actually, I will not be able to answer this question.
Okay. Sanjay here?
Saudhu, I did not hear what you did you say.
Okay, I'm explaining again. It's the classical situation which we face usually. So Munoz G tilde is U and H tilde is K. Okay. So you look at the Riemannian symmetric space G tilde mod H tilde. So this is like our G mod K. I'm saying that this G tilde mod H tilde Muna has shown is essentially G, right? It's the same space. Look at the differential operators on G tilde mod H tilde, which are left invariant under G tilde and right invariant under H tilde. Now, since G tilde H tilde is a Gelfand pair, this algebra of operators is commutative. Muna did not say G tilde H tilde is a Gelfand pair. I am saying it. So you can take it on faith that yes, it's a Gelfand pair. Now, this algebra of operators which you got, it is analogous to our dg mod k according to Helgerson's notation, right? That is a commutative algebra of differential operators. According to Muna's identification, those differential operators are coming from differential operators on G, certainly. Am I making sense?
Yes.
So, which operators? I don't think it is whole of UG. It should be some subset of UG. Which one it is? Sorry for the botheration.
No, that's okay. This is a nice question. Actually, the thing is, there is a result that this probably I am telling for others. I am not telling about you. So GK is a Galfand pair. So if there is any molecular automorphism theta, so that theta x belongs to this inverse double coset of this x, right? So if you want to prove that result, so and if we want to show that something is GK is a Gelfand pair, you want to get a hold of this theta, and in this situation which we are discussing, that theta is really this Cartan involution. Mithunda, are you there?
In other words,
But it
what
is just
I'm
diagonal.
Yes,
in other words, what I'm trying to say is that suppose somebody proves a result for functions on G tilde mod H tilde, let us some result about functions on G tilde mod H tilde.
Yes, sir.
Maybe a result of Fourier analysis, maybe a result of geometry, whatever.
Yes, sir.
That basically means the person has proved a result for functions on G.
Yes, sir. Yes.
But is it fall on this Riemannian symmetric space? I mean, this H is compact. Is it Maxwell compact? I mean that diagonal.
We will show that in this case it will be actually, I think, Maxwell compact.
But
no. Just
I thought it's semi-simple.
No.
Spaces.
No. Sorry. Because the group itself is compact. If this group is G tilde, for instance, this compact. Okay. So there is no Maxwell compact. We cannot say. Galfand pair, you can really say.
If you think of this symmetric spaces of compact type where you deal with U, theta, and K, right?
Yes, sir.
And then you look at the fixed points, you call it K, you look at U mod K, you do analysis there.
Yes, sir.
That your G tilde is actually U, H tilde is actually K.
Yes.
So when you are doing that UK analysis, inside that analysis, whole analysis of G is actually hidden.
Yes.
But Sagatotha, if it is non-compact G, then it is fall in the semi-simple symmetric.
I'm not talking about non-compact. I'm saying for compact symmetric spaces, anybody who has proved a result on U mod K has actually proved a result on G.
D.
So, yeah. But which result proved? I mean.
No, for Pelli-Wiener theorem, this is the case. Actually, Angela, they first proved this for G tilde, H tilde, and after that, people prove for general case. So for Pelli-Wiener theorem, this is the case.
So then Ingham.
This is why I was asking. This is exactly the we need the class of differential operators.
So, sir, do you know the answer? This. Mitunda Swagat sir.
No, actually he doesn't. I think. Yeah.
Just stop the recording. Rajesh, you have joined later. It seems.
Yeah, I joined 5 minutes later. So should I stop it?
राजेश को
Yeah.
लेट फाइन क्या राजेश
राजेश क्या?
Late.
मुना
लेट
Oh,
में आ रहा हूँ
मिथुन
नहीं हो रहा हूँ तो कैसे चलेगा
अरे सॉरी 5 मिनट्स लेट हो गया.
अरे कोई बात नहीं. रखता हो यार.